Let us start. Let us start the remaining portion of the bending stresses. Now, I have gone through the different axes of the bending stresses, which have proved that the sigma divided by y is equal to m divided by y is equal to u divided by r, where sigma is the bending stresses created in a fiber at a distance y from the neutral axis, and m is the bending moment created on that particular section under our consideration. I is the moment of inertia, E is the Young's modulus, and R is the radius of bending of this of the concerned beam under bending or negligible shear stress. We have discussed that ratio I divided by y, where y is the ratio I divided by y, where I is the farthest or the most important distant point of the section from the neutral axis is called section modulus. So I is the moment of inertia is all right, but where here the conception section modulus will be applied only when for the fiber which is the farthest away from the neutral axis. We have discussed that each bar due to the action of a bending moment, a bar will be under a position or under a condition of bending, which will bend, and the innermost fiber will under maximum compression, and outermost fiber of the beam will be under maximum tension. And there will be a plane throughout in the cross section of the beam where there is no such tension or compression. That particular beam is defined as the neutral axis. And in all our calculations, we consider the stress of the particular fibers which are away from of a certain distance from the bending moments. Here, this distance is given as y. So, and here the definition of the section modulus, this distance y is the distance of the farthest or most distant part of the section from the neutral axis. So, the definition of section modulus gives us the moment of inertia about the neutral axis, first of all, divided by the distance of the farthest point from the neutral axis. Thus, m is equal to sigma I divided by y, or sigma into z, where z is the section modulus concerned. The moment of residence, the maximum bending moment which can be carried out on any section which can be carried out by a given section for a maximum value of stress is defined as the moment of resistance. So, for a given value of maximum stress, as per the design condition of the concerned beam member, So the beam can sustain a maximum amount of stress, and the maximum bending moment which creates this amount of stress is defined as the moment of resistance. Now next comes the moment of inertia. The moment of inertia of a resisting body is obtained by summing up the product of various particles with the square of the distance from a given axis. So what is the difference by definition? There are the various particles, the products of various particles, or if products of various infinitesimal area or differential area with square of the distance from a neutral given axis is defined as the moment of inertia, or only area multiplied by the distance is defined as first moment of inertia. Area multiplied by the square of the distance also defined as the second moment of inertia, or on simply moment of inertia. So as you know, from the definition of section modulus, we are supposed to know the moment of inertia of the beam, as well as the equation of bending, which is the equation of bending, which is, in order to know the bending stress, we also know the moment of inertia, as we are supposed to know the bending moment of the beam on the constant section, and the Young's modulus, and the radius of the curvature. So we are supposed to calculate the moment of inertia, which is important to know the bending stress of the beam. This is called bending equation of beam. Now, what is the moment of inertia just appeared? Next, you have to find out the moment of inertia of different type of cross section. The moment of inertia about any axis parallel to the centroidal axis is equal to the moment of inertia through the central axis plus the product of the area of the figure and the square of the distance between the two axes. So we have to know the centroidal axis means axis through the center, axis through the centroid, and the moment of inertia of our constant axis is supposed to be parallel to the central axis, and the moment of inertia about our axis is supposed to be equal to the moment of inertia through the central axis plus the product of the area of the figure and product of the area of the figure and square of the distance between the two axes. So first we have to know the moment of inertia about the central axis, Next, we have to know the area of the figure and the square of the distance between the two axes. Next, area of the figure and multiplied by the square of the distance, the distance of our axis from centroidal axis. So you have to know the moment of inertia of the central axis first. Then we can only have the distance. Then we can only have the area of the figure, our constant total figure, as well as to the area of the axis, area distance from the axis to center of our constant axis to the centroidal axis. So moment of inertia of various section is supposed to be given like this. So you have to calculate the following way. The rectangle, consider the elementary strip, say delta A, delta Y, of thickness delta Y, at a distance Y from the XX. Then the moment of inertia about the centroidal axis XX is supposed to be the Y square B into dy, where B is the width of this rectangular section and dy is the width. Delta y is the dy or delta y is the thickness of this elemental strip. This means with the area of the elemental strip multiplied by the square of the distance from the neutral axis. Thus, the moment of inertia of the centroidal axis is d squared divided by minus d plus d by 2, means distance from the central axis xx to one side, that is d by 2, and another side, that is minus d by 2, and it is to be integrated between the distance of the constant strip from the square of the distance of the constant strip multiplied by the area of the constant strip, which gives us the product of the area and the square of the distance between the square of the distance from the central axis. First of all, so one thing we have told the total the moment of inertia through the central axis plus the product of the area and the square of the distance between the axes. So here we are getting product of the area square of the distance multiplied by the product of area, means we are integrating the full for integrating for the minus d by 2 to plus d by 2 means integrating to know this product of the area multiplied by the product of the area multiplied by the square of the distance from for the whole section. So we know b is the constant. So from minus d2 plus d2 y squared dy or y cubed by 3 might integrated from minus d2 by 2 or b to the power 4 divided by 12. Thus, by parallel axis theorem, we know the integration, the moment of inertia about the axis AB is equal to Ixx plus area into x square. So Ixx moment of inertia about the central axis is thus obtained by b d squared divided by 12 or b d cubed divided by 12 plus area b into d means total area multiplied by the distance from the from the central axis, that is d by 2 whole square. So bt cubed divided by 3. So this equation gives us the from the parallel axis theorem, means this theorem, this is the parallel axis theorem defined as is. First of all, we have to find out the moment of inertia about the central axis, which we have calculated here. Next, we add it with it the cross-sectional area multiplied by the distance of the constant fiber. We are saying that distance of the constant fiber is the extreme fiber, that is AB, at the end of the rectangular section. So this is the distance is given here by the square of the full area divided by the distance, which is x square, which is given as d divided by 2, means half of the width or the half of the height, half of the depth of the beam. So this square. So if we add BD cube, so if we add them together, we'll get the moment of inertia about the of the line, the straight line. If a point of view about any axis, about the axis AB from the central axis. The section modulus we know Ixx divided by y max. The maximum distance is y by 2, and Ixs is the moment of inertia about the neutral axis, that is b cubed 2 by 12, that is bd squared divided by 6. That is the section defined of section modulus, which is given here. The moment of inertia about the neutral axis divided by the distance from the farther point. We know for the rectangular section, moment of inertia of the neutral axis goes through the line xx, which is thus also the central axis. Next, let us go for rectangular or hollow cylinder. Now, for the rectangular hollow rectangle about the central axis xx, what we have to find out first the moment of inertia about the central axis or about the neutral axis. Here also neutral axis is xx for the symmetry of the figure. So xx is bd cube, b to the power 3 by 12 minus b to the power 3 divided by 12. Capital B means the which shown in the figure, the width of the outside of the rectangular section. D is the depth of the outer of the rectangular section, outer section, and small d is the inner width of the inner section, and small d is the depth of the inner section. So here the difference between these two central axes will be the axis, the moment of inertia about the neutral axis, that is bd cube minus bd capital B multiplied by capital D to the power cube is equal to small d into small b multiplied by small d to the power cube divided by 12. that is IXX, and ZXX should be in the same B, capital B to the power cube minus small b to the power cube divided by 12 divided by d divided by 2. So b to the power cube minus b to the power cube divided by 6 into t. So ZX is equal to b to the power cube minus b to the power cube into 6t. The I section about the central axis XX. XX is fine. For the rectangle, this is the section modulus, and this is the axis of the about the with the moment ratio about the neutral axis. And you can follow the same procedure if you want to know the momentum ratio about any other axis. Next, I section. Now about the central axis, we know XX said here the will follow more or less same way. The width at the outer section at the and from here, from this point right side to this side of the I section is given as capital D, and B, small b is given the width from this section to this section, and total depth from this angle to this angle is given as D, and from here to here is given as capital D, or b to the power cube minus small b to the power cube divided by 12. So B is equal to B, which is the width thickness of the wave. B is the B minus thickness of the wave. This is the wave. So, and D is the thickness of the flange. This is the flange. This is called wave, and this is called flange. So, where small b means this distance is equal to capital B divided minus thickness of the wave. This is the B, and this is the thickness of the wave. So this is the small b is given as capital B minus thickness of the wave, and capital small d is the capital D means total depth from this end to this end, we are minus 2 into thickness of the flange. Flange is, there is one flange here and there is another flange here. So there are two flanges. The twice of the thickness, individual thicknesses should be omitted from the total depth. Thus, what happens? Zx is given by bt cube minus bt cube divided by 12 divided by capital D by 2, or in the same way, bdt cube divided by minus b to the power cube divided by d into 6 into d. For a channel section, the same expressions are valid in the same manner. Next, let us go for the rectangular section. Above the central axis XX from here to here, the IXX should be b to the power 36, and about the base AB b to the power 12. IXX is the moment of inertia about from the neutral axis, and we have to follow the same procedure. We have to know the area and the distance, area of the total area multiplied by the distance of the distance from the central axis, which is equal to 2 by 3. Now, about the base AIB b to the power 12. Now, about the circular section here. The central axis XX is given here is pi to the power 4 by divided by 64, and ZX is equal to IXX divided by Y max. IXX divided by Y max is equal to pi to the power 4 by 64 divided by D by 2, and pi to the power cube divided by 32. The hollow circular section, where the outer diameter of the outer ring is the d to the power 4, so capital D to the power 4 minus diameter of the outer ring, the small diameter of the inner ring, that is small d to the power 4 divided by 64 is the for hollow circular section. For triangle, you know, that is IXS b to the power b d to the power 3 divided by 36 for circular section, pi d to the power 4 by 64, and hollow circular section pi d to the power 4 minus 64 divided by 64. And ZX is the same way. the distance of the maximum further maximum fiber, that is d by 2, is to be divided. It is to be divide the moment of inertia of the neutral axis. So this will take this particular form. Now, let us go through three practical problems. That is 5.1. The figure shows a simply supported 200 millimeter width, simply supported at both ends from here and here, 200 millimeter width. This given as this width is here 200 millimeter and depth is 300 millimeter and 4 millimeter long, 4 meter long beam. So size of the beam and cross section area is given. Determine the bending stress at the point C, where which is 60 millimeter away from the below the top surface and 1.2 millimeter from the left surface. So what is given here? Solution is simply. Now the B width of the section is equal to 200 millimeter. D depth of the section is given as 300 millimeter. W the distributed load 200 kilonewton per meter, and total length is 4 meter or 4,000 millimeter. To find the bending stress 60 millimeter below the top surface and 2.5 meter from left surface, 1.2 meter from the left surface. Here you see the point is given. Here it is depth is 6 millimeter below the top surface and this point situated at 1.2 meter from the left end. So you have to first calculate the bending moment. The reaction engine support is to be half of the total load. That is, total load is load per unit area is 200 kilonewton per meter. So it is 200 kilometer, 200 multiplied by the 4 meter of length divided by 2, because this load is equally shared by both these end supports. So this will be equal to 400 kilonewton. Now, the moment of inertia of the section is P to the power Q real as per our RDL calculations, which is given as, well, B is 200 and D is 300, which is to the power 3. So 450 multiplied by 10 to the power 6 millimeter to the power 4. The bending moment at a cross section, is R into X minus W into X squared by 2. So this cross section is the 400 is the reaction and section multiplied by X is minus, which is positive because it is taking the anti-clockwise moment, and Wx square, W into X is distributed force, which is acting at a distance x by 2 at x by 2. So if to make the moment, it will be Wx multiplied by x by 2, which is making a anti-clockwise, which is making a anti-clockwise moment, which is negative here. Thus, R into x minus Wx squared by 2, where x we know is given as 1.2. X is given is at a distance 1.2 from the left end, that is x. So we put the value of x is equal to 1.2 meter, where R is the reaction we have calculated, that is 400. So W you have know that is 200 kilonewton per meter. W, so 400 into 1.2 minus 200 into 1.2 to the power square by 2. So that is equal to 366 kilonewton per meter. So at the moment bending moment at the section X is given as 336 kilonewton per meter. The distance from the C from the neutral axis is 500 to minus 60 is 90 millimeter. So it is from the top end, it is distance is 60 millimeter, and we know the neutral axis will be passes through the center of the beam. So that is half of the depth, that is 150, 300 divided by 2, 150 minus 60 is equal to 90 millimeter. So sigma divided by y is equal to m by I, or sigma is equal to m into y, that is m, bending moment is 336 kilonewton per minute, 336 kilonewton to the power 6, that is per meter, divided by 450 to 10 to the power 6 millimeter 4, and that is multiplied by 90 is the distance C, which is given as 67.2 meter MPa, which is the bending stresses. 120 millimeter width and 10 millimeter thick steel plate is being bent. Next problem, 100 millimeter, 20 millimeter width and 10 millimeter thick steel plate is bent into a circular arc of 8 millimeter radius. So determine the maximum value of the stress produced. Also find the maximum bending moment which will produce the maximum stress is equal to 200 into GPa. A thick, that is the width of the beam is 120 millimeter thickness, and width and thickness is equal to 10 millimeter. And steel plate is bent into a circular arc of 8 meter radius. So it is bent into a radius of 8 meter. Determine the maximum value of stress produced. Also, the bending moment which will produce the bending moment will produce the maximum stress. Also, the bending moment which will produce the maximum stress. Well, E is given as 200 kPa for this particular material. So, what is width? B is 120 thick steel plate, 120 millimeter. It is a thick plate, so its width is much higher than the depth. That is 10 millimeter only. It's like a sheet of paper, a sheet of steel, and radius of curvature is 8 meter, and E is given 200 millimeter. So, for the bending stress bending equation, we get sigma divided by Y, M divided by I, E divided by R, or sigma E divided by R into Y. Well, E is given as 200 kPa divided by R. R is given as radius of curvature, that is 8 meter, is multiplied by 1,000, 8,000 millimeter. 200 in GPa multiplied by 1,000, 200 MPa, plus multiplied by Y is half of the depth of the concerned plate. So the plate where depth is 300 millimeter, so it is half of it will be, it is 5, that is 125 MPa. So E divided by R into Y is equal to 200 divided by 800,000. Thus, sigma will be given as half in 1.25 MPa. Next, we can say M divided by I is equal to E divided by R. So M is equal to E by R into I, where E is given 2,000 and R is given 8,000, 200 into 1,000. E is given as 200 into 1,000 divided by 8,000. That is 120 multiplied by the moment of inertia of the area, that is B to the power cube divided by 12. B is 120 multiplied by the depth, that is 10 millimeter divided by 12. So M will be equal to 250 into 10 into 250 to 1,000 Newton per millimeter per, or 250 Newton meter. Next problem will be a simply supported cast iron beam of 800 millimeter and 15 millimeter to 15 millimeter section falls on applying a load of 300 Newton at the midspan. So find the maximum uniformly distributed load that can be applied applied safely to a 200 millimeter width, 75 meter depth, and 1.6 long cantilever made of the same material. So what we have? We have a cast iron square beam. First of all, we have to have a cast iron square beam made of cast iron of 800 millimeter total length, and with this cross-section radius 15 by 15 millimeter. Now it falls on applying fails on by applying a load of 360 Newton at the mid-pitch. Okay. Maximum uniformly distributed load that can be applied safely to 200 millimeter wide, 7 meter deep, and 1.6 long cantilever made of the same material. So first we have to find out what is the safety safe or maximum stress which you can apply. with this particular beam, and then we can use the maximum safety of maximum safe stresses to find out the distributed loads that can be applied of the beam of different of same material of part of different dimension. Initially the simply supported beam, its width was B 15 millimeter and depth is around 15 millimeter. This is a square. That's why P width and depth are same. L is the length 800 millimeter and weight, that is central load at the midspan, means it is a point load working at the midspan, which is given as 360 Newton per meter. Now we have to find the universally applied load for a 30 millimeter width, 75 millimeter depth, and 6.1 meter long cantilever made of the same cast iron material. The moment of resistance is given as equal to moment of resistance sigma into Z is equal to maximum bending moment. So here sigma stress we applied this formula e to the power q divided by 6 is equal to maximum bending moment W into L divided by 4, which is acting at the center. So here says here sigma is equal to 15 into 15 square divided by 6 is equal to 360 multiplied by the length 800 divided by 4, or sigma is equal to 128 meter MPa. Next, what will happen to the cantilever? Its width is 400 millimeter and depth is 75 millimeter and length is 1600 millimeter. If the load be W per meter run on the cantilever to break it, then the maximum bending moment W will be WL square divided by 2. Because the maximum moment will be at the center, will be total weight will be W into L, while L stands for the total length, which is known to us, and W the specific weight, which is unknown to us, will be uniformly divided into both the end supports. That means by W, which of the supports will carry a moment where the carry a reaction of equal to W into L by 2, and bending moment at the center of the beam will be the W into L by H, W into L into X by 2, WL by 2 to X by 2, and at the half of the length L by 2, it will become WL square by 2, W 1.6 whole square divided by 2, or 1.28 W Newton meter. In the above relation, W is in Newton meter, L will be constant in consistent unit that is supposed to be in meter. The moment of the resistance is same, sigma into Z is equal to sigma multiplied by BT square by 6, which I put here as 120. Sigma is 128. We have already calculated the maximum bending moment which we can carry by this radial beam. That multiplied by the second beam, width of the second beam multiplied by the depth of the second beam, 1 to the power 2 divided by 6, and which is equal to 1400 and for 18 bending moment. So the maximum bending stresses this new beam can carry is equal to 4800 into Newton meter, 0 Newton meter. The equating the motor resistance is 1.82 here, maximum bending moment, into W is 4800, or W is a 3750 Newton per meter. Hence the distributed force of intensity 3750 Newton per meter of length. That is our answer. Now, next problem is a floor carries a load of 8 kilonewton per meter and is supported by joists that are 120 millimeter wide and 120 millimeter wide and 250 millimeter deep over a span of length of 6 meter. Determine the spacing center to center of the joist if the maximum allowable bending stress is 10 meter. So we have the floor. What we have is the floor. It can carry, it is carrying a load of 8 kilonewton per square millimeter. That is the stress it can carry, and it is supported by joist. Those are 100 millimeter, 20 millimeter width, which is given here, and 250 millimeter depth over a total span length is 6 millimeter. So cross section area is 250 divided by 100 depth is 240 millimeter divided by width is 120 millimeter, and total length is 6 millimeter. And it is 3 in number. And determine the center to center distance of the joist if the maximum available bending stress is given by 10 millimeter width. Now, the spacing of the joists, we have to find the spacing of the joists. Let the spacing of the joist is S meter. The loading on each of the joists, loading on the joist per unit length, W, area supported by the joist per unit length, multiplied by load per unit area. Area supported by the joist divided by load per unit length. The spacing of the joist multiplied by the length multiplied by the load. Spacing is given as S, but load per unit area is 8,000. Given as 8,000 is load carrying 8,000 kilonewton per square meter. So 8,000 Newton per means 8,000 into S Newton per millimeter. Now, moment of the resistance, maximum bending moment will be W L square by 8,000 into S multiplied by L square, where 6 is the length of the each of the joist. We are by 8. So 36,000 S in Newton meter. The moment of the resistance, sigma multiplied by the section modulus, dq by 6, that is 10 into the allowable bending stress is 10 MPa. So we put 10 here, and D is given as 120 millimeter width and 240 meter depth, which is equal to 11 sigma is 11520 multiplied 10 to the power 3 multiplied 10 to the power 3 Newton per millimeter square, or 1152 Newton meter, if we consider this in from millimeter to meter. So 11520 Newton per meter square. They're equating these two from this bending moment and this bending moment. Then 3600 S is 11520, or S is equal to 0.32 meter or 320 millimeter. So next problem, let us start discussing, because we have seen more times. A 200 millimeter into 800 millimeter I-beam is to be used as a simply supported beam of 6.75 meter span. The web thickness is 6 millimeter and the flanges are of 8 millimeter thickness. That determines what concentrated load can be carried at a distance 2.25 meter from one support, and the maximum permissive stress is 8 millimeter MPa. So the cross-sectional area of the I-beam is 200 multiplied by 800 millimeter I-beam. It is that is depth that is the width is equal to 200 millimeter and depth is equal to 800 millimeter I-beam. Is used. It is used as supported, simply supported beam of simply supported beam of 8.75 millimeter. The web